subscribe to our YouTube channel, Joy Learning TV.
Hello there, you're welcome. This is your Senior High School Hour on your Joy Learning channel. I'm happy to be in your company one more time. Thanks for letting me into your home, your offices, your school, and wherever you're watching this from. Today, I have the pleasure of bringing you another beautiful mathematics experience, elective maths, particularly for those of you in your second year in the senior high school. And of course, for every other person who intends to refresh their minds or to learn it for the first time. This is the third and concluding part of our series on coordinate geometry. In our first part, we dealt with the straight line. In the second part, we dealt with the circle. Today, we shall be treating coordinate geometry and we'll be dealing with the parabola. The parabola. Well, you've heard the word para in many things, including paracetamol or paramilitary or para something. Well, parabola is an interesting shape in mathematics. It's part of what we call the conic sections. In conic sections, we have right circular cones, two right circular cones, usually. And depending on where the plane cuts the right circular cone, it would assume a shape. So for example, if the right circular cone were cut so that the plane is horizontal and perpendicular to the axis, we would have a circle. For a right circular cone that has been cut in such a way that it is parallel to the plane, to the vertical plane, would have maybe an ellipse and many others. Well, the parabola is one of those sections of a conic shape or a right circular cone or two right circular cones, better put. Today we shall not be dealing with conic sections in particular. We'll be dealing with the parabola as a part of the coordinate system, and that's why we have coordinate geometry. So this is the third part. Well, we hope at the end of this study together that we'll be able to do a number of things between you and I. Number one, we hope that you should be able to clearly, very, very clearly, define a parabola. You'll remember we defined a circle. We said a circle was what? Do you remember? Okay. I give you a second to try. What's a circle? By our previous definition. Well, I give it to you. A circle is the locus of all points equidistant from a fixed or reference point. We're going to be defining a parabola, and you should be able to understand why that definition is important and what we use it for. The second thing we'll be achieving together is we should be able to determine the equation of a parabola given relevant parameters. And we should be able to find those relevant parameters given the equation of the parabola. In other words, we should be able to move from left to right and from right back to left. We love to do that in math. We love to be able to negotiate our way in multiple directions. And finally, we should be able to determine the tangent to a parabola and the normal to the tangent of that parabola. Speaking of which, we will be going a few steps back into our previous studies. And like I mentioned, this is the final of a three-part series. In our first part, we dealt with the straight line. In the second part, we dealt with the circle. And now we're dealing with the parabola. So we shall be borrowing things from the previous lessons, and if perchance you were not able to join us, well, visit our YouTube channel and refresh yourself on that, or else just dust those textbooks and you should be good enough to go with us. We shall do something else besides going a few steps back. I'll probably take you a step into the future. What that means is I'll borrow from a concept from a topic you might not be familiar with. It is important, so we will not go too deeply into that topic, but it will be something you can appreciate. So let's define a parabola. What's a parabola? By definition, by coordinate geometry definition, or the definition of conic sections, a parabola is the locus of points equidistant from two things, from a point, which we'll call the focus, and from a line, which we'll call the directrix. Let's take that again. A parabola is the locus of points equidistant from a point and a line. The point it is equidistant from, or they are equidistant from, is called the focus, and the line is called the directrix. So, keywords, locus. Like in our treatment of circles, we say the circle is also a locus. Well, the word locus is Latin in origin, and it means place or position. For the purpose of math, I would prefer, as a personal preference, to call it a path. P-A-T-H, a path. So I could say that it is the path of points. So if we have points that are, if you like, if points were beings and they were dragging their feet or walking, you could trace their path. And if you trace their path, it would describe a geometric shape. In the case of a circle, it would describe something that is always at equal distance from a particular point all the time. For a parabola, it would be equal from two different points. Because of this definition, we would go a few steps backwards. Now, let's look at our Cartesian, for example, x and y coordinates. Now, if we had a point, say P, as you can see on your screen, if we had point P, and the coordinates of point P was A0. You know why it's 0? Because it lies on the x-axis. So the value of y there is 0. If we had that point P, and we had another line, Q, and the line Q falls on the point negative A0, you would notice there is some similarity here. First of all, both are on the same line, x. But something more. The point P has coordinate A, and the point Q has coordinate negative A. In other words, if A were, say, 5 units, it would mean that from the origin to point P, 5, from the origin to Q will be negative 5. It means they will be equal distant, and that's where we get the term equidistant. Now, if we had more of such points, so say we had another point there, it would be exactly between P and Q, the red point there at the origin. Now, if we had other sets of points, as you can see on your screen, then if these points obeyed this rule such that at every point, let's say point R, if the distance between P and R is the same as the perpendicular distance from R to point S. So if PR was equal to RS for each of the points there, so the point beyond R, which is just ahead of it, if that point was, say, point Q or point L, it will mean that PL will be equal to L, maybe V. And you would notice that since the distance from P to Q is equal to the perpendicular distance from the point to the line Q, which is the directrix, so the line Q is the directrix, the point P is the focus. If the distance were the same all the time, we would have an interesting shape. Look at the path it is creating. So we would have that shape. You notice that? Now, that shape we have there is called the parabola. Let's take it one more time. So we said that if the distance from the point P to the line was the same all the time, so if the distance from this point at the origin was equal to point P, and the same perpendicular from that point to Q, and all the other points obey the same rule. So for example, point R had the same distance PR being equal to RS, then we would have a shape that looks like that. And that shape is called a parabola. Look at it carefully. You would notice it looks like something. Well, the most obvious something it will look like is something in electronics. Well, your camera phone or your camera has a parabolic lens somewhere inside there. Maybe not all phones, but some do. The headlight of a car is parabolic. The lights in the stadium have a parabola of a sort. And of course, your satellite dishes are parabolic. So the parabola is an interesting and important geometrical shape. And you notice we use the word focus. It tells you it is a point of viewing. And that's why in the cathode ray tube of ancient televisions and monitors, it was parabolic. These days it's replaced by the plasma and other electronic devices. But we pay tribute to it, not so. All right, so the parabola is the locus of points equidistant from the focus and the directrix, from a point and a line. Now, we said that this is the situation. If this is the situation, if it is equidistant, then we need to recall a few things. Remember, from point P to point R, we can find a distance or the magnitude. So recall something from coordinate geometry 1, where we discussed the magnitude of a line. Remember that? Yes, we said x2 minus x1 all squared plus y2 minus y1 all squared, all square root. Remember that? The square root of x2 minus x1 all squared plus y2 minus y1 all squared. Then we have point R to the line Q perpendicular. Now that reminds you of something also in coordinate geometry 1, when we try to determine the perpendicular distance of a point from a line, in this case from point R to line Q, the directrix. So two things we must recall. So let's get back to it. We said that if we had the point R and we had the line AX plus BY plus C equal to 0, and we could draw a perpendicular from R meeting at a point P, then there will be a perpendicular there 90 degrees at P, and so we should be able to determine the length PR or D. And we said the formula for that is the absolute value of AXR plus BYR plus C divided by the square root of A squared plus B squared, where XR, X subscript R, and Y subscript R are the coordinates of the point. A, B, and C are the coefficients of the line written in the AX plus BY plus C format. So A and B are coefficients of X and Y. C is the constant term. Do you recall that? If you have forgotten, just take a note of this. So that's the first thing. The second is that we said that the magnitude of a line, like I mentioned earlier, is the square root of x2 minus x1 all squared. I'm saying x2, but properly it should be x subscript 2 all squared plus y subscript 2 minus y subscript 1 all squared. So you can find the magnitude, the modulus, or the length of a line. We need those two because recall that we have 2 points and from a point to a line. That's the definition of a parabola. So we say that the line AB could be given as the square root of that, or AB squared is the square of that square root part. So you notice on the right side, we no longer have the square root sign because we have squared both sides. All right. So for this parabola, we are going to find the magnitude of PR and the length, the perpendicular distance from R to Q. So we have the length RS, more or less. But we don't have coordinates for S because it could have been anywhere. So we'll have to deal with the line. Okay, so we said RP should be equal to RS by the definition of a parabola. The locus of points equidistant from a point, which is the focus, and a line. So the point is R and P. So RP, that length, should be equal to RS. And if 3 is equal to 3, then 3 squared should be equal to 3 squared. In other words, RP, line segment RP, squared should be equal to the square of the line segment RS. Now, let's see how it works. So, what is RP squared? Differences between the coordinates. X minus A, all squared, plus y minus 0, all squared. That gives us the first part. So we have RP squared. The right side, RS, line segment RS squared. Remember, this time around, we're dealing with a point and a line. The point is R, the line is line Q, the directrix. So we're going to use that formula A, X subscript R plus B, Y subscript R plus C, divided by the square root of A squared plus B squared, all absolute value. The absolute value means that we are not regarding negatives. So for example, if I asked you the distance between your house and your school, you could say 5 meters. You wouldn't say -5 unless you meant to say you were walking backwards. All right, so the negative tells us direction. For absolute value, we disregard the negatives. So here, our A is 1 because this directrix can be written, and just a small note here, directrix can be written as X is equal to -A. Alternatively, we could write it as X plus A equal to 0. So in this case, you notice the coefficient of X is 1. There is no Y, so it is 0. And A is A, or C is A in this case. So we have 1x, usually we would not write 1x, plus 0y, which we would not normally write, plus A, divided by 1 squared plus, this ought to be 0 squared. So we should have 0 squared there. Now, 1x is x, 0y is 0, plus A all squared. So we would progress, we would have our left-hand side still intact, and then we would have x plus 0 plus A all squared, because 1 squared plus 0 squared will give us 1, and the square root of 1 is 1. If you divided any number by 1, you should get the number back. So we have this situation. Now we're expanding it. Why are we doing this? It's because we have defined a parabola, but we need a mathematical equation to define it as well. So if we expand the left-hand side, we'll have x squared minus 2ax plus a squared for the first side. Y minus 0 is essentially y. So y squared gives us y squared. You would observe I have skipped a step. So I did not say x multiplied by negative a multiplied by x. I have skipped that step. So I have straight away x squared minus 2ax plus a squared plus y squared equals x plus a all squared gives me x squared plus 2ax plus a squared. Again, I have skipped a step. I challenge you to fill that step up. All right. So if we were to group like terms or group terms, we should eventually have y squared equals 4ax. And this is our standard formula for a parabola. Take a very quick note of this. Y squared equals 4ax. Remember what the a is. The a, we got it from that point P. So the a is the coordinate, the x coordinate of the point P. All right, so we now have a definition, an English definition for a parabola, and we have a mathematical definition for it. So y squared equals 4ax. So we have achieved our first goal of being able to clearly define a parabola. All right, now look at this. We have this as a parabola. So we could have a parabola that looks this way, but is that the only kind of parabola we would have? No. We can have other types of parabola. So this time around, our point P was in the positive x-axis. We could have it on the other side. We could have P on the negative x-axis. So we could have P be negative A0, so that the directrix is the opposite of it, A0. Quickly note that in the first case to your left, P was A0. To your right, it is negative A0. And the Q value, the directrix, for the first was the negative of the first, so negative A0. But this time around, in the second part to your right, it is A0. So it's always the negative of the focus. So the directrix lies exactly on the opposite side of the focus. That's why the definition says they must be at equal distance all the time. All right, but there are more. In both cases, they were on the x-axis, but it could have been on the y-axis, like that. So it could have been upwards or downwards. So one step back so that you take a note. So in this first case, you had it this way and that way. In the second case, you had it up and down instead of left and right. So let's view all four. We have them that way. In the first case, our formula will be as we found it, y squared equals 4ax. But in the second case, because we have flipped it, we have y squared equals negative 4ax. Do you remember something about reflection in the y-axis, reflection in the x-axis? Yes, we have just reflected the first parabola in the y-axis. So we now have y squared equals negative 4ax. We could reflect again. This time around, we could have the parabola opening upwards. In our first case, top left, we had it opening to the right, opening westward, or eastward, sorry. In the second case, the parabola opened westward. This time around, it is opening upwards or northwards. And in the last case, bottom right, it is opening downwards or southward. So we have the equation will change. When it's opening upwards, we have it's no longer y squared, it becomes x squared equals 4ay. Remember, the first time it was y squared equals 4ax. But when it's opening upwards or downwards, x will begin. X squared equals 4ay. And remember what the a stands for. The a is always indicative of the coordinate of the locus, 4ay. And then we have the last being x squared equals to negative 4ay. This time around, we have reflected the third one in the x-axis. So notice again that the coordinates of the focus changes. For the third, that is bottom left, you have P being 0a because it's in the positive y-axis. For the last one, the coordinates of P is 0, negative a because this time around, the focus is in the negative y-axis. Take a very quick note of these four. You could do a quick sketch. I'll give you a few seconds to do that if you have not already done that. It's important that you understand this because if you recall, we said you should be able to determine the equation of a parabola given relevant parameters, and you should be able to determine those parameters given the equation of the parabola. So it's important to know how the parabola behaves. So let's look at a few features of the parabola, of a standard parabola that is. There are some that aren't standard. So first of all, the origin satisfies the equation. So when you put 0, 0 into the equation, it should hold true. So if you put x as 0 and y as 0, on both sides you would have 0. So 0 squared equals 4a times 0. We'll give you 0 on both sides. In other words, this particular parabola will pass through the origin, as you would have noticed in the previous cases. They all pass through the origin. You see that? All right. So it will pass through the origin. Number 2, the axis will be the tangent. Since it passes through the origin, the axis will be a tangent to the curve. We'll talk about tangents some more. Now, what's a tangent? A tangent is a line that touches a circle or a curve at only one point. So the axis will be tangent, and the parabola will be symmetrical about the axis, depending on which axis. If it is opening upward and downward, then the axis will be, the symmetrical axis will be the y-axis. If it is opening left or right, then the axis of symmetry will be the x-axis. Understand these tricks because they are useful, especially in multiple choice problems. And then the parabola extends infinitely. So for example, in the first case, it opened up eastward and it could have remained open. It would not close. It would just remain open throughout. Unlike a circle that is closed, a parabola opens and opens infinitely. So long as there are values, it will keep opening. And that's why it's good and useful when designing lights, because you can have a light as bright and as far-reaching as you would want. So it extends infinitely or to infinity. And the parabola and its tangent coincide at the vertex. We will talk about point of tangency. So the parabola and its tangent meet at the vertex, its point of tangency. All right, we have a problem here that I have solved. I'll take you through it. The question says, find the equation of the parabola whose focus is 5 on 2, 0, and the directrix is 3x minus 5. So we're supposed to find the equation of a parabola, and we're supposed to use two parameters, the focus, 5 on 2, and the directrix, 3x minus 5 equals 0. What do we do? Remember what we did. The length of a line equals to the perpendicular distance from a point to a line. So the line will be x minus 5 on 2 squared plus y minus 0 squared, or square root, equals the absolute value of 3x minus 5, because the directrix has been given to us. So 3x minus 5, there's no y value, divided by 3 squared plus 0 squared. 0 because y is absent. If we did that, we would have, and we squared both sides, we would have x minus 5 on 2 all squared plus y minus 0 all squared equals to what we have on the right squared. So we have 3x minus 5 divided by 3 squared is 9, 0 squared is 0, so we have 9. And we can square them now. All right, when we do this, we can now expand. If you expand that and multiply through by 9, our final answer should be 36y squared equals 60x minus 125. That is the equation of a parabola whose focus is 5 on 2, 0, and whose directrix is 3x minus 5 equals 0. Let me run you through it one more time. What do you do? Remember our equation. We said the length of the line joining the focus and an arbitrary point should be equal to the perpendicular distance from that arbitrary point to the line, the directrix, because by definition, a parabola is the locus of points equidistant from the focus and the directrix. All right. Another example. So say we had a focus 7 on 3, 0 and a directrix 3x plus 7 equal to 0. How do we handle it? Same way. And if we dealt with it that way, we should have a parabola whose equation is y squared equals 84 on 9x. Of course, you could convert 84 on 9 to decimal if you are required to do so, but this is safe to do. Or else you multiply through by 9 again, and you get what we had at the top here. You will have 9y squared equals 84x, if that's more convenient for you. All right. How do we find the focus and the directrix given the equation? We've been able to find the equation of the parabola given the parameters focus and directrix. What if we're given the equation and we're supposed to find the focus and the directrix? How do we do that? This is how we handle it. So with a typical question like this, find the focus and the directrix of the parabola with the equation y squared equals 18x. So now we have the equation. We need to find the focus, the coordinates of the focus, and we need to find the equation of the directrix. What do we do? Well, the first thing to do is to compare the equation you are given to the standard equation. Remember that our standard equation will have our focus as A0, or different variations of it depending on where it's opening, and the directrix will be x equals negative a. So when we compare, remember we said that y squared is equal to 4ax. So in our original question, we have y squared is equal to 18x. What that means is that 18x is equal to 4ax. So 4ax equals 18x, or 4a equals 18. Well, if we make a the subject, we have a to be 9 on 2. You could convert it to 4.5 if you please. So we now have a. And remember, since we have a, the other must be 0. Should I take that again? Yes, I would. Compare the equation you are given to the standard equation, which is y squared minus 4ax. Just compare them. If you, perchance, you do not have your original equation that way, try to make it look like that. And an example or two will help you very soon. So when you compare, you have 4ax equals 18x, or 4a equals 18. So a must be 18 divided by 4, which broken down to its lowest terms will give you 9 on 2. So our coordinate for the focus will give us 9 on 2, 0. And remember that the directrix will be the exact opposite of the focus. So our directrix x will be equal to negative 9 on 2. Of course, you could do some things about it. So for example, you could multiply through by 2. You have 2x equals to negative 9 and 2x plus 9 equal to 0. That's entirely up to you, and if the question demands such of you. I mean, at this point here, you could multiply through by 2. So you would have 2x equals negative 9, and then you could have 2x plus 9 equals 0. That's a choice you make, or a demand you meet if the question so demands it. So we've been able to do two things. Number one, determine the equation of a parabola given its focus and directrix. And we have also been able to determine the coordinates of the focus and the equation of the directrix given the equation. We've moved from left to right and from right back to left. Maybe one more example we'll do here. So we have y squared equals to negative 20x, and we're supposed to find the focus and the directrix. What do we do? Again, we compare. 4a equals negative 20, so a has to be negative 5. So this time around, our focus is negative 5, 0. Automatically, our directrix will be what? X equals 5. Always the opposite of what we get on the focus. And that's it. Just simple like that. If the question was x squared equals negative 20y, you would have equated negative 20y to negative 4ay. Because remember that depending on how the parabola opens, either leftward or rightward, upwards or downwards, our equations will change. All right, so we have a typical situation. X squared equals negative 6y. This time around, we'll compare. When we compare, we would have a as negative 3 on 2. So we have 0, negative 3 on 2, because OA will now be the situation, and our directrix will be y, not x now, to now be y equals 3 on 2. So you notice it's just straightforward. Okay. Now, something to recall. We spoke about parallel and perpendicular lines in coordinate geometry 1. So just so that you take a view again. So parallel lines, what are they? We say parallel lines are lines that are equidistant from each other, or lines that have equal gradients. We also have perpendicular lines, lines that are at 90 degrees to one another. In place of the word perpendicular, we would use the word normal. Not normal in the sense of the opposite of abnormal, but normal because we think 90 degrees is normal. Well, so M1 should be equal to M2, and in the other case, the product of M subscript 1 and M subscript 2 should give you -1. That is something to recall. Also recall that we talked about the tangent of a circle. So we said a tangent is a line which touches or cuts, and I use the word cuts a bit loosely, a curve at only one point. So if we had a circle, center O, and there was a point P on the circumference of the circle, but a line ran through and cut the circle at just that one point, that line will be called a tangent. So the line AB will be called a tangent. You need to recall this because we need to go to the last of the things we will be dealing with. We're dealing with tangency in relation to a parabola. We have been able to determine the equation of a parabola. We've been able to determine that using the focus and the directrix. We've been able to go backwards. Now we want to find out what happens when a line touches a parabola at only one point. But to understand that, we are borrowing something from the circle. So we said that if we had another line that passes through the point P, so line OS passing through the point P, so that it is at right angles with the line AB, we'll call that the normal. For a circle, the radius will always form a normal with a tangent. All right. So we said that the product of the gradient of a normal and a tangent should always give you -1. In other words, M1 multiplied by M2 should be equal to -1. So if I know M1, I can find M2 by making M2 the subject. So M2 will be -1 over M1, and M1 will be -1 over M2. So the negative reciprocal of one gives the other. I take that again. M subscript 1 multiplied by M subscript 2 gives you -1. Therefore, -1 divided by either of them will give you the other one. All right. We said something about the slope. We said that the slope is rise over run, change in y over change in x, y2 minus y1 divided by x2 minus x1. We said it's also the same thing as the tan of the acute angle between the x-axis and the line. That's the gradient of a slope. All right. That slope, now I'm taking you into the future. We can call y2 minus y1 and x2 minus x1 changes in y and x respectively, because y2 is what happened when y1 changed. x2 is what happened when x1 changed. So y2 minus y1 is change in y, and x subscript 2 minus s subscript 1 is change in x. Now, you notice two new symbols over there. The first one, delta, is a Greek alphabet. It's the capital Greek alphabet delta. It refers, mathematically we use it to denote change. Change, delta y. Change in x, delta x. It has an equivalent that we write dy dx. Now, I'm taking you into the future. This future refers to something in calculus. It's a bit uncomfortable. but we need to pick it because we need to use it. So we call that dy dx. So change in y over change in x is approximately equal to dy dx. I use the word approximately because there is something in between which you would study in the future when we treat calculus. All right. So from calculus, we are told that when we have a function, and a function is defined in many ways. So we have f of x or y equals, say, a multiplied by x and the x raised to the power n. The gradient function called the slope, remember we talked about slope a while ago, called the slope or the derivative is given by dy dx equals, now watch what is happening here and watch very, very carefully. It looks confusing, but it is quite straightforward. Dy dx will be equal to the power n multiplied by the coefficient a. So we have an. So the power here, n, multiplied by an. And then we subtract 1 from the power. The power was n. If we subtract 1, we have n minus 1. So when you have a gradient function, y equals ax to the power n, the function, then the gradient function or the derivative or the slope will be an x to the power n minus 1. All right, let's take a quick example. So if I have a function 3x to the power 5, its gradient or gradient function will be 5 multiplied by 3 multiplied by x, and that x raised to the power 5 minus 1. What am I doing? I'm subtracting 1 from the power. Remember, ax to the power n, the gradient function will be an x to the power n minus 1. If I did that, 3, 5 is 15, 5 minus 1 is 4. So my gradient function for y equals 3x to the power 5 will give me 15x to the power 4. A second example. If I have y equals to 2x, 2x can be written as 2x to the power 1. So n is 1 in this case. So I have 2 times 1, an, x to the power 1 minus 1. So 2 times 1 is 1. 1 minus 1 is 0. So I have 2x to the power 0. Remember, every number apart from 0 to the power 0 will give me 1. So 2x to the power 0 is more like saying 2 times 1. So I have 2. So my gradient function for y equals 2x is 2. Final example. If I had y equals 8 as my function, and I'm required to find the gradient function, 8 could be written as 8x to the power 0, because x to the power 0 is 1. If I use the same principle of an x to the power n minus 1, I'll have 8 times 0 multiplied by x to the power 0 minus 1. 8 times 0 is 0. 0 minus 1 is negative 1. So I have 0x to the power negative 1. To all intents and purposes, that will be 0. A few things to note. You would note that whenever you differentiate a constant like 8, you get 0. All right, this is from calculus, so I have taken you a step into the future. This is only a surface of it, but it's important for what you're going to do. But there's a small part to do. Now that you understand this basic concept, all we have done here in the 3 examples here are functions that you are used to. There's another kind of function here. It is called an implicit function. In the first case, we had y equals to something, but this time around we have y to a power, or the function having x and y components. So where I have y squared equals 4x cubed. To differentiate this with respect to x, if I differentiate y squared, ordinarily I should not be able to differentiate it because I would just have dy dx. But because it is squared, I would have 2y dy dx. So I have to repeat the dy dx. And then I differentiate the right hand side, which is quite quick. 3 times 4, 12. 3 minus 1, 2. So I have 2y dy equals 12x squared. But what I really want is not 2y dy dx. I need dy dx. So I'll make dy dx the subject. If I did that, I have dy dx equals 12x squared divided by 2y. In other words, dy dx will give me 6x squared divided by y. Let's take that again. Y squared equals 4x cubed. It's an implicit function because I have powers of x, or in some situations, have x and y together. Unlike the previous case where I could differentiate with respect to x directly, this time around I have to manage a y. It's almost like living with COVID. You can't do without your nose mask anymore, or do it's uncomfortable. Alright, so if we did that, I differentiate y squared. Ordinarily, I should have had dy dx, but now I have y squared. So I'm going to have 2y dy dx. So I have to repeat the dy dx. Then I differentiate the right side with respect to x. I have 3 by 4, 12 times x to the power 3 minus 1, which is 2. So I make dy dx the subject. 12x squared divided by 2y finally gives me 6x squared minus y. Why have we done all of this? Why have we recalled parallel lines, perpendicular lines, magnitude of a line, and done a bit of calculus? Well, it's because in dealing with a parabola, we'll be dealing with tangents and normals. A tangent, remember, is tan theta, and tan theta is rise over run, or change in y over change in x. So we need to be able to understand that. And remember, tangent means that we're going to have a tangency. Remember we said that the axes are always a tangent to standard parabolas. So if we have a tangent, we need to understand how it behaves. And one way of understanding that is to borrow from calculus and from our previous lessons. So let's look at it. I have a parabola opening eastward, standard y squared equals 4ax. If I had a point on that parabola P such that a line cuts it or touches it at the point P, that line will be a tangent to the parabola at point P. That point P has coordinates x subscript a, and I prefer we change it to 1 and 1. If you leave it at a, you're fine, but you'll be conflicted soon. If we had another line passing through it that way, that line, if the angle between that first line, black, and the yellow line was a right angle, then the yellow line will be a normal, or both of them will be normal to themselves. All right, so we have y squared equals 4ax, the standard equation. If we differentiate that standard equation, now you see why we did calculus? We're going to differentiate y squared equals 4ax with respect to x. If we did that, we would have 2y dy dx equals 4a. And if we make dy dx the subject, we eventually have 2a on y. Now remember, dy dx is the gradient or the tangent. So our tangent for this line is 2a on y. So at the point P, x1, y1, dy dx will change. It will no longer be 2a on y, it will be 2a on y subscript 1. Why? We have substituted y with y subscript 1. All right. So the equation of the tangent will look like this. Remember, the equation of a line is given by y minus y1 equals m multiplied by x minus x1. Remember that? Y minus y subscript 1 equals m x minus x subscript 1. Now our m has been found as dy dx. So we're going to replace it. So we're going to have y minus y1 equals 2a on y subscript 1 multiplying x minus x1. Please keep a note of this formula. That is the formula you'll be using to find the equation of a tangent, one of them. you'll be using to find the equation of a tangent to a parabola. Take a quick note of it. If you remember this, all you need to do is to change the m with dy dx, and that's just 1. Okay. So again, we have that. And we have our equation now written very beautifully up there. But this same equation can be rewritten. So, again, pardon me, let's have our 1 there instead of a. So, if we multiply through by y subscript 1, we have the lines as you have them, y1, etc. But at this point, you will recognize that we have y subscript 1 squared, which could be written as 4ax1. Remember that y squared equals 4ax, so y1 squared should be equal to 4ax1 squared. If we replaced it down there, and we did the mathematics here, the arithmetic here, negative 2ax1 plus 4ax1 should give you 2ax1. And from here, we can factor out 2a. If we do that, we have y1 equals 2a multiplied by x plus x1. Another important equation for the tangent of a parabola. Remember, the moment you find a tangent, you can find the normal. Why? m1, m2 equals negative 1. So the moment you know one, you can quickly find the negative reciprocal of it, and you find the other. Beautiful. Indeed, I could have ended the topic here, but let's take an example. So, given the equation of the tangent to be this, the normal will be, notice that, negative ya over 2a. Of course, I said I prefer to have, instead of a, let's call it 1, so that we don't confuse it with this other a here. So that's all you do. Just flip it and negate. So, always remember, the moment you find the tangent, the normal will be negative 1 over whatever you had. And you use the same formulas. So they're almost always alike. So let's do the condition for a tangency. What would make a line cut or touch a parabola at any point? Consider two lines, or consider the line y equals to mx plus c, and the parabola y squared equals 4ax. How do we know that that line will touch the parabola? How do we know? We call that the condition of tangency. So for example, what is the condition for which somebody will contract a disease? Well, he must get in contact with a disease-causing organism. It doesn't happen by Bluetooth, you know. So we have two equations here, the equation of a line, the equation of a parabola. If we solve them simultaneously, and I have skipped a few steps, that's your job. Complete it. I just challenge you to do that. Okay, I'll give you a clue. Wherever you see y in equation 2, replace it with mx plus c, because y equals mx plus c. So if you expanded that and equated it to the right-hand side, you will get something that looks like what I have below there. All you do is to group the terms. When you have grouped the terms, you will arrive at an interesting point here. This point looks like something you're familiar with in your polynomial class. In the polynomials, we said that there's something called the discriminant. The discriminant was given by b squared minus 4ac. And we said when this is greater than 0, you have real and distinct roots. When it is equal to 0, you have real and equal roots. When it is less than 0, you have imaginary roots. So that discriminant, you will notice we have it here. And from here, I can see that this is my b. I have b there. And I have a somewhere there. And this is my c. So I have b, a, and c. So if b minus ac is equal to 0, then it means my roots are equal and real. So a should be equal to mc. That is when I have expanded the second row and grouped them. I'll have a equals mc. And I challenge you to go through that process just to show you that for any line to cut a parabola, this must be true. A, which is the focus, should be equal to mc, where m is the gradient and c is the constant. In other words, the equation, or c, which is a constant, can be given as a on m. All right, this is called the condition of tangency. All right, so the equation could be given as y equals mx plus a on m. Remember, c is a on m. So in the slope form, the equation of a parabola can be written as such. Let's solve this problem, and I hate to do this, but we have to leave after this. So let's determine the equation of the tangent and normal to the parabola y squared equals 20x at the point 5, 10. So we have a parabola given by y squared equals 20x. And we're supposed to find two things: the equation of the tangent at that point P and the equation of the normal at the same point. In other words, the tangent and normal both meet the parabola at the point P, 5, 10. Let's deal with it. Our solution. We'll compare. When we compare with the standard equation, y squared equals 4ax, we'll have a as 5. Because 4 times 5 is 20, 20x will give us the original equation. So we can now use our formula y minus y subscript 1 and all of that. So we have y, and when we replace those values, you have y minus 10, which is our y subscript 1, equals a is 5. So 2 times 5 divided by y subscript 1, which is 10, multiplied by x minus 5. So we would have 2 times 5, which is 10, and then we have 10 on 10 is 1. So y minus 10 is equal to 1 multiplied by x minus 5. And if you group them, we have y minus 10 equals x minus 5. And you can write it in different ways. So we have y equals x plus 5. That is the equation of the tangent. Straightforward. What do? Just find a. There are other ways you could have done it. You could have... Let me not let the cat out of the bag. Let's find the normal. For the normal, since we know the original one was 1, the gradient was 1, we had 10 on 10, the gradient of this would be negative 1. Remember, it's always a negative reciprocal. So we just negate it. When we negate it, we have y minus 10 equals negative 1 multiplied by x minus 5. This time around, we have y minus 10 equals negative x plus 5. We group the terms, and finally, we have y equals negative x plus 15. Of course, you could write it in many different ways. You could write x plus y minus 15 equals to 0. You're still right. Just your arrangement depends on you or what the question demands from you. And look at this problem. Find the equation of the tangent to the parabola 2y squared equals 3x. Now, with this, what do? Quickly, write it in the usual form, y squared equals 4ax. If you did that, you have y squared equals 3 on 2x. If you compared, you will have a as 3 on 8. Then you can put it in the equation. And your final answer will be x minus 4y plus 6. If you are required to find the normal to that tangent, just negate the gradient here and you'll be fine. What have we learned today? We have learned that a parabola is the locus of points equidistant from the focus and a line, the directrix. And we said to do that, we need to find the magnitude of the line segment between the 2 points and the perpendicular distance from the point to the line. We have been able to do that and to reverse the process. So from the equation of a line, we have been able also to determine those essential parameters, which is the coordinate of the focus and the equation of the line. We have also been able to determine the tangent, the equation of the tangent, and the normal to a parabola given essential parameters like the equation of the parabola and a point on the parabola. We have said that the parabola is symmetrical about certain axes depending on the nature of the parabola. It's been a pleasure bringing you Coordinate Geometry 3, the last in the 3-part session on coordinate geometry. A real pleasure for me. I believe you've enjoyed it. I hope to see you again next time on this channel. Keep learning. This is Joy Learning Channel, and I have been your facilitator. Done so. Have a great day. Bye.
Subscribe to our YouTube channel, Joy Learning TV.